to Warp Drive Tech. The discussion today is about the reinterpretation of Einstein's field equations. Many of the slides used today were taken from presentations by EINSTEIN'S, as another YouTube channel, and I'd like to thank him, and you should too, for allowing me to use screenshots of his videos in this presentation. His videos are excellent and deserve your support. Please visit his channel and subscribe, or buy him some coffee so he keeps making great videos. Thank you. This is supposed to illustrate every particle having its own world line through space-time. So every particle has its own ruler and its own clock as it moves through space-time. Alpha refers to the row number and beta to the column number. And the flux of momentum, alpha, is going through a box of unit volume and constant orientation, beta. So the beta determines the orientation of the unit volume through which the flux of particles, particle momentum, is moving. Breaking down the tensor, upper left corner is the energy density, and the top row of the tensor is the energy flux, and the top row of the tensor is the energy flux, and the top row and the first column are the same values. The diagonal are the pressure, and the off-diagonal terms are the shear stress. And this 3x3 matrix is the momentum flux through the volume. This describes what the components of the energy and momentum tensor represent. If we have an electromagnetic field, for example, these three terms on the top are the energy flux, or the Poynting vectors, or the components of the Poynting vector. Since the tensor is symmetric, the energy flux and momentum density are the same, and the three diagonal components are the pressure. The top row, when we take the divergence of the top row, this represents conservation of energy. The energy density inside the unit volume depends on the rate of energy into or out of the unit volume. If we take the divergence of the second row, it's the conservation of x momentum. And taking the divergence of the next two rows gives us conservation of y and z momentum. And then this is a representation of taking the divergence of the entire tensor. And each row is equal to 0. And you can write this in a compact way that the covariant derivative of TUV is 0. And the fact that the divergence of this tensor is 0 is why it equates to the Einstein tensor on the left-hand side of Einstein's equations, because it too has 0 divergence. And here we have the Einstein equations. On the right-hand side, we have the energy momentum tensor we just discussed. It tells us all the ways that energy and momentum can stretch, twist, compress, bend, expand, or contract matter, including our rulers and clocks. But on the left-hand side of the tensor, added to the metric tensor, scaled by the cosmological constant, this tells us how space-time is curved and scaled. But this is where I believe things got confused. What these equations tell us is how our rulers and clocks will behave and the geometry we will measure when using them. Instead, it has come to be interpreted such that our rulers and clocks are rigid instruments, and it is the space and time they measure that is curved. This has led to very confused, inappropriate questions, such as how does gravity bend spacetime? What particle is mediated to bend spacetime? How do we quantize spacetime? The right-hand side of the equation can be completely described by the standard model of particle physics. There's no mysterious behavior or new information there. We understand the workings of matter in every observed reaction, and as such, we understand that rulers and clocks are not rigid. We have even measured time dilation directly. Yet, despite knowing these things, these questions persist because they are driven by an incorrect interpretation of the equations that space and time are something other than what we measure with rulers and clocks. For example, on the left, we have a null metric line element for the radial and time coordinates that give us the Friedmann equation. On the right, we have the null metric for the radial and time coordinates that give us the Schwarzschild solution of Einstein's field equations. When we compute the null path, or the radial path of light ray takes to reach the Earth, these two equations are identical. They're both expressed as the speed of light divided by another term, which we will call a refractive index. And whether that refractive index is represented by A of t or K of t doesn't matter. So we can interpret the scale factor of the universe, A of t, as a refractive index just as we do with K of t in the polarizable vacuum representation of general relativity, originally presented by Hal Puthoff. Note, the two equations are typically interpreted differently. The Friedmann equation interprets A of t to represent the expanding size of the universe, where rulers and clocks are fixed constants, rigid. Whereas the Schwarzschild solution interprets rulers to undergo length contraction and clocks undergo time dilation when inside a gravity well. These are the physical effects that give us black holes, for instance. If we were to interpret A of t this way, we would find that it is our own ruler that is shrinking locally at a rate of about 6.8 nanometers per meter per century. This equates to the Hubble constant, and it explains why it is linear over such a vast distance, because it's a local effect. I much prefer this interpretation rather than the one where the universe is expanding such that it violates conservation of energy and requires vacuum energy to constantly be created out of nothing at an ever-increasing rate to fill the new space that is being created. This view is compatible with increasing entropy and the fact that the universe is running down. The forces that sustain the length of the ruler no longer have enough energy to inflate our ruler to the size it was, say, a century ago. TUV, the energy momentum tensor, is losing energy, and as such, our rulers are deflating like a balloon with a hole in it. Hence, the farther away and back in time we look, the shorter our own ruler will appear, making wavelengths longer and giving us the illusion that everything is moving away from us. This talk was about how malleable rulers and clocks are the tools that we use to measure space-time. As such, depending on how the energy momentum tensor components are affecting our rulers and clocks, space-time can appear to be flat or curved. It is a subtle distinction, but one that instantly answers the question of how does matter bend space-time? It doesn't. Matter bends matter, and we use this matter to measure space-time. It is our instruments that give us the shape of beautifully curved space-time manifold, and this serves a useful purpose. However, the manifold is only a mathematical construct that we should never mistake as something which has been measured precisely with rigid rulers and clocks. Thank you. Click the notification bell to be notified when new content is uploaded. Be sure to watch all our videos and subscribe and give us a big thumbs up if you like this video. If you'd like to support new content and experiments, you can contribute directly using our PayPal link or subscribe to our Patreon to make monthly contributions. Thank you so much.